These are the Eisenstein primes. They're a set of complex prime numbers that are arranged hexagonally. But how do they work as primes, and where do they come from? They're a subset of the Eisenstein integers, which are numbers of the form a plus b omega, where a and b are integers, and then omega is -1/2 plus √3/2 I. And these may look familiar, 1/2 and √3/2. You may remember them from trigonometry. A 30, 60, 90 triangle has side lengths 1/2, √3/2, and 1, or something similar. And this means that if we plot complex numbers with the horizontal axis being the reals and the vertical axis being imaginary, then omega is -1/2 plus √3/2 I, which means that this angle between -1 and omega is 60 degrees. And 60 degrees is a sixth of the way around a circle, which means that omega falls on a hexagon with -1 and 1. And the other points on the hexagon are 1 plus omega, negative omega, and -1 minus omega. Now we'll take this hexagon as a starting point and extend it with more points, the multiples of 1 on a horizontal axis, and the multiples of omega on a skewed axis, and then all of the points in between. And this gives us a triangular grid, with some points, as an example, 3 plus 2 omega, and -2 minus omega. Instead of representing each integer as just a point, we could represent them as a hexagon. And this is where we get this representation, where all of the primes are colored and all of the composite numbers are in black. But how do we know what's prime and what's composite? You may be familiar with the definition of a prime number being only divisible by 1 and itself. But this definition causes problems for the Eisenstein integers. Let's go back to this hexagon of points. These numbers are units, and what we mean by units is they divide every Eisenstein integer. And that's because each of these units to the 6th power equals 1. And I encourage you to check that yourself. It's a fun exercise. But since the units to the 6 equals 1, that means any unit u divides any Eisenstein integer z, because u times u to the 5th z equals u to the 6th z, and we just showed any unit to the 6th is 1, so this is 1 times z, which is just z. So u always divides z. Any of these units divide any number. So no number is only divisible by 1 in itself. Every number has at least 6 divisors. But we could adjust the definition to say a prime number is only divisible by units and itself. And this gets us part of the way there, but we should also notice uz divides z. Z times any unit is a divisor of z. And that's for a very similar reason as the units themselves. And these numbers of the form uz are called the associates of z. They're z times any unit. So for example, here are all the associates of 3 in yellow. And so every number is divisible by all 6 units and all 6 of its associates. That is the bare minimum for divisors. So we can just define primes as having the minimum divisors. A prime number is only divisible by units and its associates. And this modified definition does give us some sensible prime numbers. So here we are back with the primes. We see here is the prime 5 plus 2 omega and all of its associates, and -2 minus omega and all of its associates. And we see that the associates always have this kind of symmetry. They always form a hexagon. And that's because the units also form a hexagon. So multiplying anything by that hexagon is going to give us another hexagon. Now, why do we care about the prime numbers? Well, one of the main uses of prime numbers is giving a prime factorization. So here we see 20 plus 10 omega has the prime factorization of 2 times 5 times 2 plus omega. Now it also has a prime factorization 2 omega times negative 5 omega times 1 minus omega, and it also has this other prime factorization. So we don't exactly have unique prime factorization, but all of these purple numbers are associates of each other, and so are all of the red, and so are all of the yellow. So if we group associates together, we do get unique factorization. Okay, and now maybe we ask, how do we find the primes? We can mimic a method that's used to find the natural primes, called the sieve of Eratosthenes, where we start with all of the natural numbers. We remove 1 because it's a unit, it divides everything. And then the smallest number is 2, so it's a prime. And then we remove all of its multiples because they can't be prime. The smallest remaining number, 3, is now a prime, and we remove all of its multiples. And then we do the same thing with 5, and then 7, but we don't have any multiples of 7 here, which means everything left is prime. And we can use the same process with the Eisenstein integers. So we start with all of the integers except for the units, and then we want to find the smallest number. So what we do is we find the smallest circle around 0 that intersects numbers. And here that circle has radius root 3, and it intersects 2 plus omega and its associates. So they are prime, and we remove their multiples. The next smallest circle has radius 2, and it intersects 2 and its associates. So they are prime, and we remove their multiples. And then we continue like this. The next one is of radius root 7, and then root 13. And we continue finding primes and removing their multiples until we're left with just primes. But let's take a look at those radii of the circles. They're all either a prime number or the root of a prime number. And this is always the case. We always get either a prime or the root of a prime, and every prime will eventually show up. So here are the first few primes. The ones that appear as a radius are themselves Eisenstein primes. 2 is an Eisenstein prime, so is 5, so is 11 and 17. And the rest, the ones that have a root, are the product of 2 Eisenstein primes. So 3 is 2 plus omega times 1 minus omega. And then 7 is 3 plus omega times 2 minus omega, and similarly with 13 and 19. And it may seem that these roots appear every other prime. 2, root 3, 5, root 7. But that pattern does not continue for very long. So what is the pattern between having a root and not? And why do we always get primes? Before we answer that, let's take a step back to my previous video where I talked about the Gaussian primes. These are primes of the form a plus bi, and they form a square grid. And we found the primes in a very similar way, using a sieve. And just like with the Eisenstein primes, the radii of all the circles were prime or the root of a prime. And it gave us the same result. Those with the root were a multiple of 2 Gaussian primes, and those without were themselves a Gaussian prime. So the Gaussian primes and the Eisenstein primes have these very similar properties, but they're not exactly the same. In the Gaussian primes, we got root 2 as a radius, but in the Eisenstein, we just got 2. And then in the Gaussian, we got 3, whereas the Eisenstein had root 3. So they don't always line up, but sometimes they do, like with 59 and root 61. So what's going on here? For the Gaussian primes, we get a root for any prime that's 1 more than a multiple of 4. So 5 is 1 more than 4, 13 is 1 more than 12, 17 is 1 more than 16, and we denote that as p is congruent to 1 mod 4. And so the primes without a root are congruent to 3 mod 4. And we see something very similar with the Eisenstein primes. We get a root when p is congruent to 1 mod 6, and no root when it's congruent to 5 mod 6. Intuitively, this kind of makes sense. The Gaussian primes had 4 units, and they're arranged in a square grid. The Eisenstein have 6 units, and they're arranged in a hexagonal grid. But can we understand this better? So we'll start with the Gaussian integers, where p is congruent to 3 mod 4. Now this was the case where p itself was a prime, and it gave us a radius of p. But how do we find the radius of a Gaussian prime? Let's say we have some a plus bi, and we want to find the radius. Well, that number is a on the horizontal axis and b on the vertical axis, and this is a right angle, so we can use the Pythagorean theorem. The radius squared is a squared plus b squared, which means this is the radius. But that's a little messy. Maybe we just want to use the radius squared. That's going to be nicer to deal with. And the term for the radius squared is the norm. And we write it like this. The norm of a plus bi is a squared plus b squared. And the norm has some very nice properties. First of all, the norm is multiplicative. It distributes over multiplication. So this means that the norm of any alpha times the norm of beta is equal to the norm of alpha times beta. The other nice property is that the norm is always an integer. Because a and b are both integers, a squared plus b squared must also be an integer. Now, what we will show is that if p is congruent to 3 mod 4, p is a Gaussian prime. And we'll do this by contradiction. So we'll assume that p isn't a prime. And that means that we're assuming that p equals alpha times beta, where alpha and beta are not units. And so that means that the norm of p equals the norm of alpha times beta, but the norm is multiplicative, so that equals the norm of alpha times the norm of beta. And the norm of p is just p squared. So p squared is the norm of alpha times the norm of beta. But remember, the norm is always an integer. So how can we factor p squared? There's only 3 ways. Either the norm of alpha is 1 and the norm of beta is p squared, or the norm of alpha is p squared and the norm of beta is 1, or they are both p. Case 1 has the norm of alpha as 1, and case 2 has the norm of beta as 1. But the only numbers with a norm of 1 are units, and we assumed that alpha and beta are both not units. So case 1 and 2 fail. So we must be left with case 3, where the norms are both p. Okay, so we're saying the norm of alpha must be p, which is congruent to 3 mod 4. And the norm of alpha is going to be a squared plus b squared for some integers a and b. Now we notice this is congruent to 3 mod 4, which means that a and b have to be an odd and an even. So we can write them like this, with 2m being our even and 2n plus 1 being our odd. Now if we expand that, we see that these 3 terms are all multiples of 4. So that's congruent to 0 mod 4, so we can get rid of them. But now we have 1 is congruent to 3 mod 4, which is not true. We've arrived at a contradiction. And that means that case 3 also failed. So all 3 possibilities failed, which means that there is no way to factorize p without using a unit. And so p must be a Gaussian prime. And it falls on the circle with radius p. So now we understand why p being congruent to 3 mod 4 gives us a Gaussian prime. And we can use a very similar argument for the case of 5 mod 6 in the Eisenstein primes. Our equation for the norm is a squared plus b squared minus ab. And we can show that it's impossible for anything of that form to be 5 mod 6. It's a little more involved, so I won't walk through it, but I encourage you to try it yourself, and you'll want to use the fact that omega squared is -1 minus omega. Okay, what about the other cases where we get the square root of a prime? Before we go into that, I want to discuss an alternate definition of a prime number. And we'll start by noticing that if natural numbers a and b are odd, then their product ab is also odd. And this means that if AB is even, then A or B is even. They can't both be odd because then AB would be odd. And by even, what we're really saying is that they're divisible by 2. If AB is divisible by 2, then either A or B is divisible by 2. But this is also true if we say they're divisible by 3, or in fact, divisible by any prime P. And this is only true for the primes. So this works as an alternate definition for the primes. And not just in the natural numbers, this also works in the Gaussian and the Eisenstein integers. So we'll want to remember this alternate definition. We'll come back to it soon. Now what we'll do is look at the case of P congruent to 1 mod 4 for the Gaussian integers. And first, as an example, we'll take P equals 13. We can create a circle for doing multiplication mod 13. So if we want to multiply 2 times 3, we just stack up these arrows and we get to 6. Or if we want to multiply 4 times 5, we again stack up the arrows and we get to 7. And 4 times 5 is 20, but 20 is congruent to 7 mod 13. And so this circle works for any multiplication mod 13. And this works for 13, but we could make a similar circle for any prime number. So if we have some prime, we can make a circle using all of the digits less than P. And because P is 1 mod 4, all of the digits less than P is a multiple of 4. So we will get these 4 points evenly spaced around the circle. Now the point on the right must be 1, because 1 times 1 is 1, and 0 degrees plus 0 degrees is 0 degrees. Now the point on the other side must be -1, because -1 squared equals 1. And that means that that top point is some q, such that q squared equals -1. And importantly, using Dirichlet's theorem, we can say that q is prime. So we have some prime number q such that q squared is congruent to -1 mod p. Now we'll use q to make two Gaussian integers, q plus I and q minus I. And their product is q squared plus 1. Now using the congruence above, q squared plus 1 is 0 mod p. So the product of these two Gaussian integers is a multiple of p. So q plus I times q minus I is divisible by p. Now let's go back to our alternate definition of a prime. If AB is divisible by p, then A or B is divisible by p. So here, q plus I is our A, and q minus I is our B. And since their product is divisible by p, then if p were prime, at least one of them would also be divisible by p. But that's not true. If we divide each of them by p, we see that neither of these numbers are Gaussian integers. All of the coefficients are fractions. They're not integers. So neither of those two numbers are divisible by p. P fails this definition of a prime, which means that if p is 1 mod 4, p is not a Gaussian prime. And that means that p is the product of at least two primes. But we notice the norm of p is p squared. And because p squared has at most two prime factors, then p has at most two Gaussian prime factors. So it has at least 2 and at most 2, which means that p is equal to alpha times beta, where the norm of alpha and beta are both p. But the norms are both p, and we recall that the norm is the radius squared, which means the radius of both is root p. And that's why we get root p whenever p is congruent to 1 mod 4. And we can use a similar technique with the Eisenstein primes. I'll skip over some details, but in general, we take p to be 1 mod 6, and then we make a circle to do multiplication mod p. There's 1 and -1 on the sides, and then we can find some prime q, such that q cubed is -1 mod p. We can use that to show that q squared minus q plus 1 is 0 mod p. but q squared minus q plus 1 is also the product of these two Eisenstein integers. And because it's 0 mod p, that means that this product is divisible by p. But neither of these themselves are divisible by p, so p fails our alternate definition of a prime. Therefore, p is not prime, and because the norm of p is p squared, it's the product of two primes. So now we have a good understanding of the relationship between the natural primes and these complex primes. If you found this interesting, you can interact more with these primes at the link in the description with this web tool that I created. This works best with a computer rather than a phone. By default, it shows the Gaussian integers, but you can use the menu to switch to the Eisenstein primes. You can highlight an integer for more information in the bottom left. Highlighting a prime will show all of its multiples, while highlighting a composite will show all of its prime factors. And you can switch to display composite, you can change the color or the way that it's colored, turn on the grid lines. You can also color by factor. So the darkest numbers are the primes, and then the lighter you get, the more factors you have, where green corresponds to having a lot of the same factors. In the bottom left, we see this is 2 plus omega to the 5th power. And then purple corresponds to having a lot of different factors. This has 4 different prime factors. And you can also view other kinds of primes, like the ones we get if we use root -2, or root -67, or root 94. And I'll be talking about all of these in my next video.